Okay, welcome to today's tutorial. In this video, we're going to look at interference of waves, right? Interference of waves. So what is interference of waves? Interference is a phenomenon or is a phenomenon that occurs when two waves overlap in space. When you have two waves overlapping in space, that phenomenon is referred to as interference of waves, right? So interference is a phenomenon that occurs when two or more waves overlap in space. So the overlapping of waves is referred to as what? Interference of what? Of that wave. And basically we have two types of interference. We have the constructive interference and the destructive interference, right? So a constructive interference occurs when two crests or two troughs meet. So this is a crest. Crest, like I said, crest is the upward maximum displacement, right? So there are two waves here. This is the crest of the first wave and this is the crest of the other wave, right? So when two crests meet and two troughs meet, trough is the trough is the downward maximum displacement, right? Is the maximum downward displacement. So this is a trough. This is another trough for the other wave. So when two crests meet or two troughs meet, that relationship or that overlap is referred to as what? A constructive interference, right? Is referred to as a constructive. So this is a constructive interference. Constructive interference occurs when two crests, this is a crest, this is a crest, or two troughs, this is a trough, this is a trough, when they meet, right? Then we have the destructive interference. And this is an example of a destructive interference. So a destructive interference occurs when a crest meets a trough, right? So this is a crest, which is the upward maximum displacement. This is a trough, downward maximum displacement. So when a crest meets a trough, so they are meeting here at this particular point, right? So when they meet at this particular point, that is referred to as what? A destructive interference. That overlap is referred to as a destructive interference. So this is an example of a destructive interference. Why is it destructive? Because it will eventually lead to destruction of the wave. The wave will cancel out completely or partially, right? So here there is an overlap and the overlap is constructive because two crests, they meet, right? This is a crest, this is a crest, they meet. This is a trough, this is a trough, they meet. This is a crest, this is a crest, they meet. This is a trough, this is a trough, they meet. But here, this crest and this trough, they are meeting together at the same time. So that is what makes it a destructive interference, and this is a constructive interference. So these are the two types of interferences that we have. So again, a constructive interference is a form of interference that occurs when two crests or two troughs meet. And we've looked at that before. That will now make the amplitude to add up, resulting in a wave of greater amplitude, right? So the path difference is n lambda. Then the second type of interference that we have is the destructive interference, and it occurs when a crest meets a trough, and we've looked at that grammatically. So it is destructive because the amplitude will cancel out partially or completely. The path difference is equal to open bracket n plus 1 all over 2 bracket close lambda, right? So note the path differences for the two. So let's look at some questions as regards to interference of waves, right? So the first question I have here is, a person stands between two loudspeakers driven by an identical source, right? Each speaker produces a tone of frequency 155 Hz on a day when the speed of sound is 341 meters per second. The person is 1.65 meters from one speaker and 4.95 meters from the other speaker. What is the path length difference in terms of wavelength? And hence deduce the type of interference produced. So this is a very simple and easy question. So let's get into it. So the first thing I would want to do here is to fish out the parameters that were given to us here. So I read again. A person stands between two speakers. So let's say they are speaker A and speaker B, right? A person stands between two speakers driven by an identical source. Each speaker produces a tone with a frequency of 155 Hz. So the frequency of the two speakers is 155 Hz, right? On a day when the speed of sound is 341 meters per second. So the velocity of that wave is what? 341 meters per second. That's the velocity of the sound wave, right? The person is 1.65 meters from one speaker. So let's say this is speaker A, this is speaker B. The person is 1.5 meters from speaker A. So let's put here 1.65 meters from speaker A and 4.95 from the other speaker. So speaker B, the person is 1.95 meters away from speaker B. Then the question is, what is the path length difference in terms of wavelength? And hence deduce the type of interference produced, right? So the first thing that we're asked to look for here is to look for the path length difference in terms of what? Wavelength. So first of all, we know that V, velocity, is equal to what? F lambda, right? F lambda. So if our V, velocity, is equal to F lambda, our wavelength, which is lambda, will be equal to V over F, right? Lambda will be equal to V over F, right? So my lambda will now be equal to, the velocity of the wave is 341 meters per second divided by the frequency, which is 155, right? So if I bring out my calculator, 341 divided by 155, that will be equal to 2.2. So my wavelength is equal to what? 2.2 meters, right? This is my wavelength. Then the path difference. What is the path difference? So the path difference, which is the next thing I'm going to look for. So this is my wavelength, right? So the path difference is the next thing I'm going to look for. The path difference will be equal to the difference between the person's distance from speaker B and speaker A, right? So that will be B minus what? A. So that will now be equal to 4.95 minus 1.65, right? 4.95 minus 1.65 will be equal to 3.3, right? 3.3 meters. So this is the path difference. So the question was to look for the path length difference in terms of wavelength. So the path length difference in terms of wavelength, lambda, will be equal to the path length difference, which I will refer to as delta. So the path length difference is delta, right? Over what? Lambda. So that will be equal to 3.3, which is the path length difference, divided by 2.2, which is the wavelength, right? So this is the path length difference in terms of wavelength. So 3.3 divided by 2.2, that will be equal to 1.5, right? So that will be equal to 1.5 lambda. This is the path length difference in terms of wavelength, so, right? So the next question is, hence deduce the type of interference. So the type of interference that is produced is a destructive interference. Destructive interference. So why is it a destructive interference? It is a destructive interference because the path length difference in terms of wavelength is a fraction, 1.5. So this is a decimal, right? So that was what makes it a destructive interference. So here it's very important that you should know that if the path length difference is a whole number, for example, if it is 1 lambda, if it is 2 lambda, if it is 3 lambda, and so on and so forth, that interference will be a constructive interference. But when it is a fraction, for example, 0.5 lambda or 1.5 lambda or 2.5 lambda, so that interference is referred to as what? A destructive interference, because the path length difference is, in terms of wavelength, is a fraction. So if it's a whole number, it is constructive. It's a fraction. In this fashion, it is what? Destructive. So let's look at the next question that we have here. And the question is, two loudspeakers are driven by the same signal generator, producing a tone of 170 Hz. On a day when the speed of sound is 340 meters per second, a person stands 2 meters from one speaker and 4 meters from the other. Calculate the wavelength of the sound. B. Determine the path difference in terms of wavelength, and state the types of interference produced at the person's position. So that's a very simple question as well. So let's get into it. So this question is similar to the first one. Two loudspeakers are driven by the same signal generator, producing a tone of 170 Hz. So the frequency of the sound, right, of the tone is what? 170 Hz. On a day when the speed of the sound is 340 meters per second. So the speed of the sound, the velocity is what? 340 meters per second. A person stands 2 meters from one speaker and 4 meters from the other speakers. So the distance of the person from speaker A is what? From speaker A is 2 meters. The distance of the person from speaker B is what? 4 meters. Then the first question we have here is calculate the wavelength of the sound. So we know that V, velocity, is equal to what? F lambda, right? So if V is equal to F lambda, our velocity is what? Our velocity is 340, equal to our frequency is what? 170 Hz, times what? Times your lambda, which is your wavelength. So if we make this wavelength the subject of the formula, our wavelength will now be equal to 340 divided by 170, right? So if we divide 340 divided by 170, that will be equal to 2. So the wavelength is equal to what? 2 meters. This is our wavelength. Then, so this is our question A, right? We've answered question A here. Calculate the wavelength of the sound. So this is the wavelength of the sound. Then B, option B, is to determine the path difference in terms of wavelength and state the type of interference produced at the person's position, right? So the path difference will be the path difference, which I will represent as delta. This is the path difference, is equal to the distance of the person from speaker B and the distance from the person from speaker A, the differences between the two distances, right? So that will be 4 minus what? 2. That's B minus what? A, right? So 4 minus 2 will be equal to what? 2. So that's 2 meters. This is the path difference, right? So, but what we're looking for is the path difference in terms of wavelength. So the path difference, which is our delta, in terms of the wavelength, is equal to the path difference divided by what? The wavelength. So that will be equal to, our path difference is what? 2. 2 divided by what? The wavelength. The wavelength is what? 2. So 2 divided by 2, that will be equal to 1 lambda, right? So this is the path difference in terms of wavelength. So the next thing is state the type of interference produced. So the type of interference that is produced is a constructive interference. And why is it a constructive interference? It is a constructive interference because the path difference in terms of wavelength is a whole number, 1 lambda, right? So, like I said before, if it is a fraction such as 0.5, 1.5, 2.5, 3.5, 4.5, that will be a destructive interference. But if it is a whole number, the path difference in terms of wavelength, if it is a whole number such as 1, 2 lambda, 3 lambda, that interference should be a constructive what? Interference. So this is a constructive interference. So just a quick recap on this. Interference is a phenomenon that occurs when two waves overlap. And we have two types of interferences. We have constructive and destructive.